So welcome everyone to the day 4 of 2 questions of physics per day series. So we are going to solve question number 7 and question number 8. So 7 says that a particle moves along a orbit which is r equals to a cos psi under the influence of a central field Fr. So we are required to find the r dependence of the force. So the particle follows a planar orbit described by r equals to a cos psi, which depends only on r and psi. So we are required to write we have a as the constant and the motion occurs under a central force which is of this nature, that is its dependence is on the radial distance between the two masses. So we are required to find the radial dependence of the force. So we know that in this is a very simple and beautiful question where we directly apply the Binet's equation for the orbit, which helps us to find the radial dependence, r dependence. So we know that r is equal to a cos psi. R is equal to a cos psi. So we define a constant which is inverse of r, and it is equal to u. So u is equal to a 1 by r, which is equal to alpha sec psi, and alpha is itself the inverse of a given in the question. Okay. Now this is the Binet's formula, which is h square u square in the bracket double derivative of u with respect to psi plus u. So we now know that we are required to find the double differentiation of u with respect to psi. So this is the single differentiation of the u, and this is the double differentiation of u, which is alpha sec psi in the bracket tan square psi plus sec square psi. So now we know that tan square psi plus sec square psi can be further simplified, and we could have the all the we could substitute all the required expression in the Binet's formula to arrive at minus h square alpha cube sec cube psi within the bracket tan square psi plus sec square psi plus 1. So we know that tan square psi plus 1 is sec square psi. So in this bracket we could have 2 sec square psi. Okay. So which will ultimately lead us to 2h square alpha cube sec to the power 5 psi, and we know that u is equal to alpha sec psi. So sec psi is nothing but u by alpha. Okay. So when we substitute all the values, we finally get that minus 2h square u to the power 5 divided by alpha square. This is how the function f looks, and we know that u is nothing but r. So we finally get minus 2h square divided by alpha square multiplied by 1 divided by r to the power 5. So we now know that this central force is inversely proportional as the fifth power to the distance, which is given by this expression. Now we have the eighth question, that you have to establish that for catching up the higher speed, a rocket should burn fuel as quickly as possible. Okay, this is a very beautiful question of the rocket motion of the rocket, which has often been asked by UPSC in mechanics. So we are aiming to show that rocket should burn its fuel rapidly to achieve higher final speed, particularly when launching in the gravitational field. This is a problem in rocket dynamics under a constant external force where the gravity opposes the motion. We analyze this situation using the modified rocket equation in the presence of the uniform gravitational field given by this expression, where the external force mg is equal to m times dv by dt minus u dm by dt. Okay. So you know that u is nothing but the exhaust velocity, which is relative to the rocket, and it is given by this particular expression. When you assume that u and g are constant and both are directed downward, okay, because the rocket is going upward, then u will be downward because it is velocity of exhaust, and gravitational constant is obviously in the downside. Okay, so this is going to be our equation. Then we integrate it and get that integrated from t0 to 2 final. T0 is the time 0 and t final is the time final. So we get this expression. And when you put t is equal to 0 for v is equal to 0, you finally get this expression. Okay. So rocket is starting at the time 0. So when rocket is starting, its initial velocity is going to be 0 as well. Okay. So this particular expression turns that final velocity is u ln m0 divided by mf minus gtf. Okay. G is gravitational constant, is final time. That means for the what time rocket has been on or it is burning the fuel. So this expression shows that the final speed Vf consists of two terms, u ln m0 divided by mf and minus gtf. Okay, so critically the gravity term increases the longer the burn takes. Okay, so That means you have to burn fuel as quickly as possible. So TF has to be as less as possible for the greater, as less as possible for greater speed. That's it. That is the quantitative interpretation from the final velocity formula. Okay, so conclusion that in the presence of gravity, the final velocity of a rocket is reduced by a term proportional to the burn duration. Thus, to achieve the greatest possible final speed, the rocket must burn fuel rapidly, minimizing the time spent under the gravitational deceleration. That means higher speed.